So this is not in your notes, but I want to kind of go through this and show you real quick. So the energy levels, we talked about it yesterday. I don't know like how clear it was, so I just want to kind of do a quick little refresh on it. Obviously, we understand that the nucleus is the center of the atom and that the electrons form circles around that nucleus. Sometimes we'll call them energy shells, levels, layers, but here's our nucleus, here are our energy levels. You have the very first one. It is so small that you can only fit 2 electrons, okay? All the other levels, here, 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 and if you need more, those can all hold 8, okay? And I'm simplifying this. In chemistry, you'll get into it deeper, but for hydrogen and helium, 2 is all it can hold. All right, so 2 is full. So that's why helium is over there with the noble gases that are just sitting there on their donkeys, right, doing nothing, because they are stable and satisfied. All the rest, once this first energy level is full, then you start adding electrons, okay? You add another one for lithium. You add another one for beryllium, all right? And so it's the number of electrons in the outermost level that determines which group or which column they get put in, okay? And so I have a few examples that I'll show you. So the first energy level is small, so it can only hold the 2, right, like I showed here, only hold the 2. And so once those 2 are filled, that level is done, you add the next level. All right, so here's what helium would look like. That nucleus is really big, but this is helium. The first energy level is full, it has 2. That 2 fills the valence, so that's why it's a noble gas. And then we have to add an energy level, all right? Once we add the next energy level, we start by adding 1 electron. That, once the energy level is full, all the way on the right side of the periodic table, you drop all the way back to the left and go to the next row to start lithium. So if you look at your periodic table, right, you have hydrogen and then helium. Helium is full with 2. It drops down, you go to lithium, Li. So lithium is in valence group 1. Valence group 1 means it's going to have how many valence electrons? Oh, trick question. Valence group 1. 1, right? Genius. Who said it? Way to go, Garrett. Okay. So valence group 1, right? And so that would be like over here, 1 electron out there. And then we look at beryllium, valence group 2. How many valence electrons? 2. So now lithium would have 2 in that outer level, okay? And so it keeps getting filled up until you would go all the way across. Boron would have 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and then you would get to neon, and neon would have 8. Once you get to neon, it is full. You have to drop back down to all the way to the left, to the next row, or that next period, to sodium. Sodium would start back over at 1, and then 2, and then 3. And so you just kind of keep filling those levels. And so here's lithium. Lithium is in valence group 1, so it has that 1 electron out there. Now, I get that it's a total of 3 electrons, but we're not looking at the total. When I say valence, you're thinking just the outer layer, okay? And so lithium has 1 out there, and then beryllium has 2 out there. Notice that the 2 are still on the inside. Those stay put. Here are our electrons on the outer valence for beryllium. Then we have boron. Boron is in valence group 3. 1, 2, 3 on the outside. That's why it's in valence group 3. And then so on as you go to carbon and nitrogen and oxygen and fluorine, until you finally get to neon. So here's neon. 1, 2, 3, 4, 5, 6, 7, 8 in that valence. Since neon is now full, that outer layer is satisfied, that's when the table kind of, there we go. The table kind of readjusts. You're at the very end of period 2, you would drop back down and start period 3 with sodium. And then it would look kind of like this. This layer would be all the way full, and you would be moving into energy level 3. okay? So I just wanted to kind of, explain that a little bit more, show you a few more visuals and pictures to hopefully, make a little bit more sense. Again, you can see the two are always gonna be filled if it's anything bigger than helium. And so those two are there, and then you start adding in the electrons. And so it's really simple. You have valence group 1, 2, 3, 4, 5, 6, 7, and 8. Helium, even though it only has 2, is stable and full, so that's why it is with the other noble gases that are full at 8 electrons. So helium's that special one. These are called our transition metals. Sometimes I call these the short stack, meaning they're not the tall columns. These are the tall columns. The valence groups are set, and that's why those electrons are there. The valence groups or number of electrons are not set for these ones, and that's why they're left blank. All right, and so they could be, they could have 2, 3, or maybe even 4 electrons in their outer layer, and that would have to be told to you. All right, so a lot of times I'll say, ignore the short stack, or, you're looking at your tall columns for your valence groups. But whatever valence group they're in, that's the number of electrons that they have. Here's something that I want to point out too. If you look, let me see, where'd that periodic table go? Oh, I might have, sorry, I have too many of them there. All right, if you look up here, you have 1, 2, 3, 4, 5, all the way to 18. You have to include these transition metals when you are counting the overall groups, because there's 18 total columns, okay? If you look at your periodic table, notice how in my handwriting at the top, in little circles, I have 1, 2, I skipped the transition metals, and then I have 3, 4, 5, 6, 7, and 8. Those are the valence groups. But you'll also see the little numbers that are typed on there, 1 through 18. So you might have caught on yesterday that I was saying valence group 8 or group 18. So if I'm talking about the noble gases in group 18, I also know that this is valence group 8. And the reason why it's 10 off is because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those transition metals. So if I go group 1, group 2, and that's also valence group 1 and valence group 2, but when I get over here, this becomes valence group 3, not 13, valence group 4, not 14. It's because these are not valence groups. And so basically it's like 13 minus 10 makes this valence group 3. 14 minus these 10 makes this great valence group 4. And so once you get to this side of the table, the valence group is 10 less than the overall group. And you can see that if you look at your paper. Here it's 3 and 13, 4 and 14. So there is a difference. If I say valence group, it's not the same as, if I say valence group 3 or group 3. Well, this is group 3 right here, but this is valence group 3. So there's a difference. So you have to be very clear what you're asking. I have to be very clear what I'm asking or saying. So if you need something, if you ever aren't sure, like, was that valence group or was that just regular group? Okay, and that's just kind of the way it is. And again, it'd have been easier if these were predictable too, then they would have been included as valence groups, but they're not, right? But it does make it stand out. It's kind of nice that they're short and like they do stand out. So we know we're skipping these, not that they're unimportant, but that they're not predictable. I can't tell you if this iron is going to be a 2, a 3, or a 4 for its valence. I don't know if that chromium is a 2, a 3, or a 4, right? I would have to tell you that if you were using it in a problem or something. Okay? All right. So, I'm going to just double check, make sure there isn't anything else I want to just kind of rehash with you. So again, notice 1, 2, skip all these, 3, 4, 5, 6, 7, 8, right? But this would still be valence, this would just be regular group 3, regular group 4, regular group 5. But this becomes valence group 3, 4, 5. Okay, I think what I would like you to do, I'm going to go ahead and stop this.